Ladies and gentlemen, welcome to the third part of this webinar exploring the transition from analog to digital electronics in physics experiments.
The second group of algorithms we are going to analyze is composed by the DPP-QDC and DPP-PSD. They are often embedded in the same FPGA firmware. The DPP-PSD/QDC firmware is designed to capture charge pulses, typically much faster than those used for the DPP-PHA. In fact, in most cases, these are anode signals from PMTs and do not pass through a charge-sensitive preamplifier. The pulse generally has a duration of a few nanoseconds, sometimes a few tens, but rarely exceeds 100 nanoseconds. Energy information is contained in the charge of the pulse, that is, in its area. For this reason, the digital algorithm implements the gated integrator function, which sums the samples within a gate that is automatically generated by the algorithm through a leading edge discriminator or a constant fraction discriminator, CFD. It is also possible to disable the self-gating function and use an external gate, or program coincidence or anti-coincidence between external and internal gates. Thanks to the FPGA's memory buffer, it's possible to introduce a delay on the signal, allowing integration of the pulse component that arrives before the discriminator triggers. All parameters for integration, such as discriminator threshold, gate duration, and position, are programmable. In addition to energy measurement, which represents the total charge of the pulse, the algorithm performs a shape analysis, calculating the ratio between the fast and slow components of the signal. For this purpose, the integration algorithm computes a double integral, one over a long gate to capture the total charge of the pulse, and another over a short gate to capture only the fast component of the signal. Consequently, the slow component, the tail of the signal, is derived through subtraction between the total charge and the fast charge. Finally, the PSD parameter is obtained as the ratio between the charge in the tail and the total charge. The PSD parameter provides information about the signal's shape and can be used for discriminating the type of particle that interacted with the detector. For instance, it allows discrimination between gamma rays and neutrons in a liquid organic scintillator. The digital discriminator, both leading edge and CFD, is used not only to generate the integration gate, but also to calculate the timestamp, so the arrival time, of the pulses, thus completing the multiparametric analysis composed of three quantities: energy, so the charge, shape, and time. To achieve good timing resolution and minimize walk, which refers to the threshold crossing point shifting with signal amplitude, the technique of constant fraction discriminator, CFD, is employed. Its operation in the digital version is much like the analog version. An attenuated copy of the signal is created according to a certain fraction, along with a delayed copy. The second copy is then subtracted from the first one, resulting in a bipolar-shaped signal with a zero crossing that occurs at a constant time, independent of the signal's amplitude. In the digital version, the delay is achieved using memory cells, and attenuation is a simple multiplication by a programmable parameter. To enhance resolution, interpolation between ADC samples is used to pinpoint the zero crossing position with much higher precision than that given by the sampling period. This gives rise to a coarse time, determined by the sampling clock, and a fine time that indicates the exact position within the clock period. Naturally, the ADC's sampling frequency should be appropriate for the speed of the signal being read. As a general rule, for effective interpolation and resolution, you need at least 3 points on the leading edge, preferably 5. This implies that if you want to read a pulse with a leading edge of 5 nanoseconds, you require a digitizer with a sampling rate of 1 gigasample per second. However, through suitable calibration techniques, it's possible to optimize the interpolation algorithm even in cases where signals have edges equal to the sampling period or even faster. For instance, signals produced by a barium fluoride detector, which have edges below 2 nanoseconds, when read by a 14-bit, 500 megasample per second ADC, with proper calibration done on the signal shape, a better resolution of 100 picoseconds can be achieved.
The third section of this webinar is now completed. Stay with us for the last part.